Okay, so this is the review document for exam 3, and I've marked off some questions in the review document on my hard copy. So what I'll do is just go down and pick out the ones that I've looked at. And there's Justice. Okay. I'll pick out the ones that I've looked at, and maybe even as we pass them, I may see a couple more, but I know I want to hit these for sure to cover all the topics that will be useful for passing the exam. So we're going to start with number 1. And considering this equation, hydrogen iodine yields 2 hydrogen iodides. That's solid. Oh, no, it's gas. Gas. Okay. And now, just to make the point, when we write equations for equilibrium problems, the state of the reactants and products is important because of the way that an equilibrium equation is constructed. The law of mass action is only valid for reactants and products that change their concentration during the reaction and are required to change in order to reach equilibrium. So that lets pure liquids are out, solids are out, because their concentrations do not change during the reaction. Of course, they're consumed or they're produced. You know, that hasn't changed. I mean, the Lavoisier's law of conservation of mass is still valid, but the expression of equilibrium only depends upon the concentrations. So in this case, the only 2 components that change their concentration are hydrogen gas and hydrogen iodide gas. So now let's get to the question. Which of these statements about this equilibrium is false? So we're looking for, we're going to see all of these are true except for one. A says if the system is heated, the right side is favored. Now that's a tricky one because nothing is said in the equation. Nothing is said in the equation about heat production or absorption. We don't know if it's exothermic or endothermic. So we have to make some assumptions in order to answer that part A. And in order to do that, we've got to look at what would we expect this type of equation to be. Is this going to absorb energy, or is the product going to be lower in energy because of the relative energies of this side to that side? If these are higher energy total than the product is, then we would expect to be exothermic. But the other way around, if the energy in the product is higher than it is in the reactants, then we would expect it to be endothermic. I can't say. I'm looking at my worked problems to see if I made some assumption here. All right. The assumption I've made there is I've invoked the collision model, in other words, kinetic molecular theory, to say that the reaction rate should increase if we increase the temperature. We get more frequent collisions. And in that case, we would say that Increasing temperature means we have to put energy into the system. So based on that argument, we would say it's endothermic. In which case, if we heat it, the right side is favored. But in all honesty, we can't say that. A could be either way. So this, in my estimation, this is a bad question because it doesn't give you enough information. And one of those selections here, A through E, is not enough information. If that were true, if there were not enough information, then I would pick that one, because A cannot be rightly judged based on the information we're given. We have to make assumptions. All right, so let's set A aside and look at the rest of them. See if there's one, B through D, that is actually false. This is a heterogeneous equilibrium. Yes, it is. Aside from the fact that our K value is actually this expression, like that, all of the components in this equilibrium are not the same phase. And even though solid iodine doesn't enter into the equilibrium, it's still active in the reaction. So we've considered this a heterogeneous equilibrium. If the pressure on the system is increased by changing the volume, the left side is favored. Now, in this case, we do ignore the solid because the pressure only has an impact on gases. Liquid solutions, solids, anything else, pressure change has no effect. So we look for, what does the pressure do to the concentration of the reactants and products? If we decrease the volume, then we are actually increasing the concentration of this gas and that gas at the same time, which is a disturbance in the equilibrium. When that happens, the equilibrium is going to respond to produce fewer. It's going to decrease the concentration of the total to mitigate that increase in pressure. So that would favor the lower moles of gas, right? Solid doesn't count. This is 1, that's 2. The reaction is favored to the left. So C is also true. How about D? Adding more hydrogen increases the equilibrium constant. What have we always known about equilibrium constants? The key word here is constant. If you don't change the temperature, the constant is that. It does not change. So adding more H2 increases the equilibrium constant is false. It doesn't change the constant. Now, it does change the equilibrium position. So the concentrations of reactants and products will change, except for the solid, of course. So there's a distinction between equilibrium constant and equilibrium position. The constant doesn't change, so D is false. And that means E should be true. Removing HI as it forces the equilibrium to the right. That is true. We're continuously decreasing the concentration of HI. So when you do that, the reaction moves to the right to replace the HI. Okay, that was 1. And D is definitely false. In fact, D would be the best answer if you're presented with this problem. A is sort of wishy-washy. There's no way to tell. So, like all multiple choice questions, if you're faced with a difficult choice, choose the best answer. All right, let's see. Yeah, pick number 2 also. So let's go down to number 2. Which of the following is true for a system whose equilibrium constant is relatively small? Okay, So if we say that, let's just take a hypothetical. Say we have that, and now the K is equal to that expression. Okay, if K is very small, say it's a lot less than 1, what does that mean about the equilibrium as expressed in this hypothetical? That means that the products are very small relative to the reactants in concentration, right? So the equilibrium tends to be toward reactants. Okay, so now let's look at the choices. Which of the following is true? So there could be 2 of them true, right? Because we have that E selection. It will take a short time to reach equilibrium. Okay. Does equilibrium say anything about the kinetics of a reaction? You could argue that it does, simply because at the microscopic level, forward and reverse reactions are equal in rate. But the equilibrium itself says nothing about how long it takes for the reaction to proceed, to reach equilibrium. I mean, after all, the oxidation of diamond exposed to oxygen is favored to be carbon and oxygen to react with one another and produce carbon dioxide. That's the thermodynamic. That's the equilibrium position. Favors the production of carbon dioxide when diamond is exposed to oxygen. But the kinetic reality says that that reaction will take thousands and thousands and thousands of years. Okay? So there's a difference between equilibrium and kinetics. They're related at some level, but macroscopically speaking, the equilibrium constant itself says absolutely nothing about the rate of the reaction, how long it will take to reach equilibrium. So A and B are false. C, the equilibrium lies to the left. Okay? If this is very small, that means that the denominator is large, the numerator is small, which favors reactants. So C is true. And D is the converse. Equilibrium lies to the right. They can't both be true. C and D are mutually exclusive. So that means C is the only right answer for this one. Okay, let me see. Did I pick? Yeah, I picked B3 also. Okay, I don't think I'll need this equation because we've got one of our own here sitting there just waiting. So let's look at number 3. Okay, for this reaction, carbon dioxide gas, hydrogen gas combine in equilibrium to produce carbon monoxide and water vapor. Okay, and we can tell from this delta H, the enthalpy, remember from first semester, that's a plus sign, which means what? The reaction is endothermic. That is, for our equilibrium qualitative assessment of this reaction, delta H is a reactant. Right? It goes in from the reaction side. So we have our delta H plus our
CO2 plus our
Hydrogen? Yeah.
hydrogen produces carbon monoxide plus water vapor.
Okay.
And this value is 42 kilojoules.
Okay. Now, we're told that K equals 1.6 at 1260 K.
So if K equals 1.6 at a temperature of 1260
K.
what is this expression though? Let's just write it out. Carbon monoxide, everything's to the first power. All right, so that's convenient. Water, and then we have CO2 and hydrogen.
Okay, that's equal to 1.6. If we're given the starting conditions of 0.15 mole each of all reactants and products.
Right. So each one of these is 0.15 molar.
Per liter, right? A mole of each one in a 1 liter insulated vessel. So what kind of system is this? We go back to thermochemistry. What kind of system is this? If the vessel is insulated, then our system is isolated, right? So everything that happens in Vegas stays in Vegas. Everything that happens in that vessel stays there.
So each one of these is 0.15 molar.
All right. So we got all our facts down. Now the questions. I assume we're looking for which one is true. Yeah, which one of these statements is true? All right. As the system comes to equilibrium, so which way is it going to move? How do we know? Calculate Q, right? What is Q? Q is this, only not at equilibrium, right?
So we would have to calculate Q is equal to 1.5 times 1.5 divided by 1.5 times 1.5, right?
So Q is equal to 1. That was easy. Q is equal to 1. And what does that mean? If Q is equal to 1, 1 is less than 1.6, which means this is too small and that's too large. So that means it's going to move to the right. The equilibrium is going to move to the right, and when it does, it takes energy with it. And our system is isolated. So when it takes that energy with it to the right, it's going to absorb some of that heat. So the temperature will decrease. Right? So what are our choices? Look at the temperature part of each of these questions. Decrease, decrease, remain constant, increase, increase. So C, D, and E, we can throw out right now, right? They can't be right. C through E cannot be correct. It's only A or B. Then we look at the other parts of the answer. What about the mass of CO2 would increase, the mass of CO2 would decrease. If it's moving to the right, CO2 would decrease, which makes B the answer. Okay? I find it helps to write all that information up on the board in a logical sequence. This may be proper English, but it doesn't help you solve the problem very, very much. You have to extract that information from word problems. in order to make sense and actually solve the problem. Okay, let's see. Yep, I want to look at 4, 5, and 6, which are each based upon this hypothetical reaction. 2 A's as a gas is in equilibrium with 2 B's plus 1 C. Okay, we might be able to do this one without writing it on the board. What about, in this case, the K is given as 10 to the 4th, 1.6 times 10 to the 4th, which means the reaction is way to the right. You might not even be able to detect any A left over. Well, you must be able to, otherwise you couldn't do the K. Not with what we know now. There are other ways to calculate the K, of course. Okay, addition of B to an equilibrium mixture of the above will what? Well, it'll definitely cause A to increase, right? It'll move the reaction back to the left. It'll consume some of the C also. So those two are possibilities. So what are our choices? Causes the concentration of A to increase? Yeah, that's true. How about B? Cause C to increase? No, we just said it'll cause C to decrease. Have no effect? That's false. Cannot be determined? We just did it, right? None of the above. Okay, so the only good answer out of all those choices is A. Causes A to increase. It shifts the equilibrium back to the left because we added some reactant. How about at a higher temperature? Oh, we're given a new K value. At a higher temperature, K is equal to 10 to the minus 5th, right? So at a higher temperature, the equilibrium shifts back the other direction. Now it favors reactant. I think we will have to put this one on the board. Right?
So our equation okay, and our K then would be B squared times C over A squared.
Okay, at our first temperature,
at K T1, we have 1.6 times 10 to the 4th. At K T2, we have 1.8 times 10 to the minus 5th. And T2 is greater than T1.
okay. So this reaction, right. If the temperature is higher and the equilibrium is shift back to the left, that means that the reaction is exothermic, right? If you put your energy term over here, and then you increase that term, then that tends to shift the equilibrium back over here. And then when we recalculate the equilibrium, we get smaller this and greater that, which gives us the smaller value. So we can deduce from this information that the reaction is exothermic. Okay? Now that we know it's exothermic, what would happen if we put the mixture in an ice bath, lowering the temperature? If it's exothermic and we lower the temperature, then that shifts things back to the right. Okay? So that means we're going to consume some A and produce B and C. So it would cause B to increase. A would not increase, A would decrease. B would increase. So that's why the answer there is B to number 5. I know we had to go around the barn a couple of times to get that answer. But if you're so inclined, if the K value decreases upon increasing temperature, that means you have an exothermic reaction. I think that one of those videos that we showed during the lecture made that point. So if it were endothermic, then increasing the temperature should increase the K. Because K does change with temperature. When we use Le Chatelier's principle and put the heat term on one side or the other, that's a qualitative assessment without saying anything about the K, the actual K value. But the K does change when you change the temperature. Okay, raising the pressure by lowering the volume of the container. What will happen then? Well, let's see. How many moles of gas do you have? On this side, you have 3. On this side, you have 2. So if you increase the pressure, the system is going to respond by decreasing the number of moles of gas. So increase the pressure, you shift things back to the left. That means A will increase. And we have the similar number of choices here. Have no effect, cannot be determined, one of the above. That should be none of the above. That's an error. Because one of the above is the same as A. That should be none. I need to correct that. Okay, any questions so far? I know I'm moving at a snail's pace, but since we have the time, I want to be sure I hit all these points adequately.
Dr. Blythe.
Yep.
So this exam is going to be due the Monday after spring break, right?
Correct.
Okay. Just
Yeah.
wondering.
You got all spring break to prep. And then when we come back from spring break, on that day that we meet again, we'll hit acids and bases. In fact, I'm going to squeeze 2 chapters into that lecture just so we can end the semester on time. But they're similar topics, and I think they've meshed back well together. We discuss acids and bases, and then we talk about the equilibrium of acids and bases, which leads to the discussion of buffers. Just a teaser. Okay, let's see. Do I have, yeah, 8. We're going to look at 8. Pardon me for a second. That's my son's cat making all that racket. She wants him to come do something and he won't listen to her. All right, so let's get back to our topic here. So we're basing the question 8 is based upon this reaction, right? Well, surrounding. What we have here is a complex ion, cobalt, which is surrounded by 6 waters and retains, since all the waters are neutral, we still retain the charge of the cobalt ion, which is 2+. Okay. When that happens, when we add cobalt-2 chloride to water, that's instantly what happens. Right? When you have equal amounts of cobalt and chloride, well, actually 2 moles of chloride and 1 mole of cobalt, that addition to water forms this complex ion and releases these chlorides. So that's where you start. But if you add more chloride to the solution here, then you start to favor the production of a different complex ion. The tetrachloride cobalt 2+, right? Since you have 4 minuses in those chlorides here, they neutralize the 2 cobalt charges, positive charges, and you have 2 minuses left over from the chlorides. That's why the charge on the total changes. Okay, and then you free up those waters that were bound. Now, the waters, of course, since this is aqueous solution, the water has absolutely nothing to do. It's not part of the equilibrium expression. Now, because you're in aqueous solution, and it doesn't say that there, and it should. We should have put aqueous here, aqueous there, and liquid here. That's an oversight on my part. So, which statement below describes the change that the system will undergo if we add hydrochloric acid? Well, what are you adding to that mixture with hydrochloric acid? This is one where the dissociation is complete. You're adding protons and you're adding chloride ions. This equilibrium expression has no place for protons, for hydrogen ions, right? So that is a spectator. But when you add chloride, now you're adding reactant. And the solution that was once pink now turns blue, or bluer as you add more chloride. Okay? So, it should become more blue? Yes, A is true. It should become more pink? No, they're mutually exclusive. Can't be blue and pink at the same time. It can't become blue or pink at the same time. So B is false. The equilibrium shifts to the right. That's also true. Another way of saying A is C. And of course, D is the opposite of C, so that can't be true. So that means 2 of them are true. A and C are both true. They're describing the same thing, one in terms of the color and the other in terms of actual concentrations. So easy answer. Okay, let me see. I picked out number 9 also. So let's take a look at number 9. We may even look at 10, since they're both based upon this same reaction. We'll start with number 9. And the reaction is 2 hydrogens plus some diatomic element yields two dihydrogen whatever, Xides. Dihydrogen Xide, that's it. Okay, so addition of X2 to this system would do what? If you add that into it, let's see, these are all gases, right? Gases. I left out the energy, plus energy. So we know this reaction is exothermic. So if we add X2, this is conditional for question number 9, then what happens? It will cause H2 to decrease. Yeah, right? The equilibrium shifts to the right and consumes some of the hydrogen. Cause X2 to decrease. That's where many students make a mistake. We have increased the X2 value. So what happens? the reaction shifts to the right using some of that X2 to change the equilibrium position. Changing the equilibrium position does not consume all of the added X2, only some of it. Once equilibrium is reached again, you still have a little bit of X2 that you added left over. So X2 actually increases even at equilibrium. Will have no effect, cannot possibly be carried out. Those are both false statements. H2X will increase. Right? So the only one that's valid for 9 is A. What if we add argon to this system? Right? Argon is a inert gas. It does increase the pressure, does it not? Right? According to brain freeze. I'll carry on. If we add argon to this equilibrium, it increases the pressure, but does it change the concentration of reactants or products? The answer is no. By adding the argon, we change the pressure, but we don't change the concentration or the partial pressures. Right? We don't change the partial pressures of the gases. So it would have no effect on the equilibrium. All right. Let's see. Number 11. Which of the following statements is true? See, I don't need this anymore. Okay. When two opposing processes are proceeding at identical rates, the system is at equilibrium. That's the definition of equilibrium. When the rates, the forward and reverse rates are equal, you have equilibrium. Are any of these others true? Well, let's look at the selections. None of the above are true. We got one that's true, so E can't be right. And there are none down here that say 2 of the above, or 3 of the above, or whatever. So we've got our answer. What if we look at the other choices just to, for teaching purposes, let's put it that way. B, catalysts are an effective means of changing the position of an equilibrium. Catalysts do not change the equilibrium constant or the equilibrium position of a reaction. Everything else being equal, the only thing that a catalyst does is get you there quicker. You reach the same equilibrium position from a given concentration of reactants, and the equilibrium constant does not change. The catalyst just speeds things up. It offers an alternate pathway, right? An alternate set of elementary steps to get you to products and equilibrium quicker. All right, so B is false. The concentration of the products equals that of the reactants and is constant at equilibrium. That's just false on its face. We know from the law of mass action that you can have a large amount of product and small amount of reactant at equilibrium, or vice versa, for different reactions. You can even change that ratio and the equilibrium constant if you change the temperature. Right? So the concentrations are, if they're equal on both sides, it's purely coincidence. It's just characteristic of that reaction. So C is false. D, an endothermic reaction shifts toward reactants when heat is added to the reaction. An endothermic reaction places the energy term on the reactant side. So if you add heat, you're shifting to the product side. So D is false. All right. So let's go to number 12. There should be a plus sign there too. A plus B. Let's see. This may be these missing terms, since they're all occurring in the graphics of each question. Well, not each, but some questions. This may be an artifact of conversion from Word document to PDF. I need to look into that. If the Word document is okay, then there's really not that much of an issue. All right, for this reaction, A plus B, you'll C plus D. You have gases A through D at equilibrium. What if you add gas A? What happens to the value of K? If you add A, the equilibrium position changes, but the equilibrium constant doesn't, because we have not changed the temperature. So as long as the temperature is constant, as long as the temperature is constant, the K value is constant. Now, why would the K change if we change the temperature? What does changing the temperature do to a reaction? We know from chapter 12 that changing the temperature changes the rate of the reaction. So if you influence the rate, and the forward and reverse rates are affected differently with a temperature change. So changing the temperature changes the relative rates of the forward and reverse reaction, which naturally changes the equilibrium position and constant. Okay, let's see. These are repetitive. We've covered those topics. Let's see. We could stop. I don't have 15 marked, but it might be worth looking into. Consider this endothermic reaction. All right. So we have 2 BrCl, gas, and that yields 1 Br2 gas plus 1 Cl2 gas. Where's the energy term? It's endothermic. On the reactant side. Okay. So we've got to make 2 decisions here in order to make a correct choice. Decision 1 is changing the volume at constant temperature. What will happen to the equilibrium? Well, you look at the number of moles of gas on either side. So we got gas, gas, gas. 2 moles here, 1 plus 1 is 2 moles there. Changing the volume does not change the equilibrium. Right? So that means the answer is either D or E. Right? See how quickly you can weed out the wrong ones? No change in the equilibrium. So it's either D or E. Now the second part, increasing the temperature at constant volume. Increase the temperature, we're adding energy to the reactant side, which produces product. Equilibrium shifts toward products. Right? So out of D or E, D must be the answer. It satisfies both conditions. Okay? Let's see, we've done one of these problems before. You know, this might be let's look at 16, right? We looked at it in terms of adding hydrochloric acid, you know, what would happen? So let's look at 16 in terms of adding, let's see, silver nitrate is added. I'm going to write the reaction out for this one. Right, that's aqueous plus chloride. Oh, there's 4 of them, excuse me. And this would give you, I'm going to have to write it over here. Cobalt, tetrachloride, tetrachlorocobalt, 2 minus, yes, 2 minus, plus 6 waters. Okay, now, and you'll see this, we're using this technique in the Le Chatelier's lab. It's called a coupled reaction. So you use one reaction to force a change in another reaction. 1 second. You guys want out? Go on. Go on out. I had to let a couple of cats out of my office. I shut the door because of that screaming other cat. So I had to let those 2 go. Maybe they had to go potty, I don't know. Okay, so this coupled reaction, if we add silver nitrate, and silver nitrate is soluble, okay, so silver nitrate, aqueous, actually produces silver ions plus nitrate ions. All right. So when we do that, what are possible reactions? What happens to the nitrate? What could the nitrate react with? I don't see anything. I suppose it could react. It's not going to react with the cobalt because the cobalt's not free. And cobalt nitrate is soluble anyway. So the cobalt nitrate would not form a stable compound of any kind, or a complex ion, right? Because cobalt nitrate is soluble. So nitrate is a spectator. The other choice is silver. What opportunities does silver have? Well, silver doesn't react with water. Silver does react with chloride. So silver reacts with chloride ions to produce a solid. Silver chloride precipitates out of the solution when we add silver nitrate. So what does that do? It removes that reactant, chloride. So it shifts the reaction back to the left. And let's see, let me put my colors back in here. This is pink. This is blue. All right, yeah, pink and blue. So the solution would become more pink because we're forcing the reaction backwards. Okay, so let's see what our choices are. It would become more blue. No, false. It would become more pink. Water will be produced. No, water's on that side. Right, we're going back this way. The silver ion will react with cobalt chloride 2 minus. No, complex ions make that chloride unavailable. It would react with that chloride ion, right? So the only possible answer here is B, makes the solution more pink. But that's why it does. And there are 2 or 3 mini experiments in Le Chatelier's exercise that I've given you for lab that use this concept of coupling reactions to induce some other reaction. So just keep that in mind when you're watching the video and trying to make sense of all that mess. All right. That was 16. And let's see, I've marked off 17 also. Let's see how far down can I go before it flips. Oop, there we go. Okay, 17. Ammonia is prepared industrially by the reaction nitrogen gas plus hydrogen gas yields ammonia. That's the Haber reaction. And for this reaction, the delta H is negative 92.2 kilojoules. And that means exothermic, right? Negative value is exothermic. K at 25 degrees is 4 times 10 to the 8th. So at 25 degrees, the equilibrium position is way to the right. Two in H3. And that's your delta H, right? Which is negative 92.2 kilojoules. So it's very energetic. Okay, K is also given. K, what's the K expression? Let's go ahead and write it out. NH3 squared over N2 to the first power and hydrogen to the third power. And that's equal to, lost my place, 4 times 10 to the 8th at 25 degrees C. Okay, so at low temperature, or room temperature, right? Actually 25 degrees, well, not for gases, but for most chemical reactions, the standard is 25 degrees C is standard temperature. And it may be for gases too, when we're talking about chemical reactions. When we're talking about physical changes or using gas laws, standard temperature is 0 degrees. Okay, so the other condition for this problem is the temperature is increased to 500 degrees. So we're going to increase this temperature to 500 degrees C. Which of the following is true? When you go from, with an exothermic reaction, if you go from 25 degrees to 500, then you shift this way back to the left. So now you have very little product, mostly reactant, and this value becomes extremely negative in that power of 10. Okay? So let's see which one answers that question. K for the reaction will be larger at 500 than at 25. Actually, it will be much, much smaller by probably 12, 14, 16 orders of magnitude smaller. B, at equilibrium, more ammonia is present at 500 than at 25. No, that's another way of saying the wrong thing. Less ammonia will be present. Moves back this way. C, product formation at equilibrium is not favored as the temperature is raised. That's true. We do not favor the product any longer. We favor the reactants when you increase temperature. How about D? The reaction of N2 with H2 to form ammonia is endothermic. Well, that's just false on its face. You just look at the sign right here. Negative, that's exothermic. Okay, so C is the answer. Historical significance here. When Haber was trying to produce ammonia for his country, just prior to World War I, and they already knew that you could take ammonia sources and make nitrates out of them. That was easy chemistry. And once you make nitrates, you can make explosives and propellants and so forth. So Haber was trying to make ammonia out of cheap sources. They could get nitrogen from the air. That was easy. They could get hydrogen from coal, which Germany had plenty of at that time, by a gasification process, and they knew how to do that too. In fact, we may have looked at one of those reactions previously. Anyway, so Haber knew that the equilibrium favored ammonia. The problem was at room temperature, even though the equilibrium was favored over there, the reaction rate was a snail's pace. The war would be over before he could make his first ounce of ammonia. So he had to speed up the reaction. And he knew to speed up reactions, you need to exceed the activation energy. That means heat. Add temperature to this side. That makes the collisions more frequent, and that makes the kinetics go that way. The problem is that term. When you increase the temperature, you may increase the speed of that reaction, but you also increase the speed of the return reaction orders of magnitude more. So he was actually favoring the reactants. Okay, so what did he do? He used finely divided iron as a catalyst. And what that did was, even though the reaction equilibrium was favored in this direction, he still got enough speed out of the reaction to get about 15% efficiency on the first pass. So if you take the stoichiometry and you say, all right, how much could we make from 100 pounds of nitrogen? Well, you can make about 15 pounds of ammonia, based upon that chemistry, high temperature with a catalyst. So how did they get it up to 98%, which it is now? Well, he had a little help, right? Carl Bosch got involved because he was employed by BASF at that time. That's an old company, BASF. And they wanted to scale it up, right? So in the process of scaling it up and working through the reactor that Haber used fit on a benchtop. It was just a tiny thing. So that was proof of concept. But to scale it up, you need huge reactors. And what he and Bosch discovered was that really what you need to do was take advantage of the different boiling points of the reactants and products, right? So the boiling point of this one is minus 195. I know that one, degrees C. The boiling point of this one is like minus, it's in the neighborhood of 250 degrees C. So it's lower than nitrogen. But the boiling point of this one is maybe minus, I forget, I think it's 35. But the temperature difference in the boiling points is huge between these two and that one. So all you had to do was run your gases through the reactor And as they come out the other side, run them through a chiller, cool them down. And this ammonia will drop out as a liquid. So you're removing ammonia from the reaction, right? Which favors what? The reaction to the right. And then they just take those gases, cycle them back through the reactor, and just keep doing that. You know, after about 7 or 8 cycles, you got 98% efficiency. But probably less than that. So that's how they solve the problem. It's a combination of kinetics and equilibrium. All right, that's 17. Let's see what's next on my list. Let's move down to 20. Oop, too far, sorry. Okay, so number 20. This reaction is allowed to reach equilibrium in a glass bulb at a given temperature. So apparently the temperature is not, the absolute value for the temperature is not important. It's just, this is what it is at this point. So we have mercury 2 oxide. Is a solid, okay? We know that's 2 minus. Does it say? No, it doesn't say. And this is 2 plus, because there's only 1 and 1. So that's in equilibrium with mercury metal, which is a liquid. So it's probably room temperature. And oxygen. Let's see, we have everything in there, gas, liquid, solid, and delta H is a positive 43.4. So that means it's going in on this side. Kilocalories. All right, calories is a measure that we haven't spent much time on. 1 calorie is the amount of heat it takes to raise the temperature 1 degree centigrade for a mass of 1 gram of water. Okay, that's all a calorie is. A kilocalorie is the same calorie that is applied to food when you eat it. Those are large calories, which are actually kilocalories. Okay, so let's back to the problem. The mass of HDO in the bulb would be increased by what? All right, we know that the only term that's in the equilibrium expression here is the gas. That's it, right? So whatever affects the production or the consumption of that gas would change these values. Okay, so what if we remove some mercury? What effect does that have on the equilibrium? Nothing, right? It's not even involved in the equilibrium. Reduce the volume of the bulb. So if we decrease the volume, there's a comparison of 1 mole of gas here and 0 moles over here. Right? Just because there's no gas over here doesn't mean it's not significant. So if we reduce the volume, we expand, decrease the pressure, decreases the concentration
of this, which means more of it is produced, right? We're increasing the volume, decrease the concentration of your gas, then the equilibrium shifts to produce more of it, which consumes the mercury 2 oxide. So B is a valid answer. That would reduce the volume. Reducing the volume would consume, wait a minute, whoa. Hold everything. The mass of HGO in the bulb let's take a fresh look at this. Oh, excuse me. My mistake. I said, let's see. I said reducing the volume, and I expanded. That would reduce the pressure. Pardon me. Reducing the volume would increase the pressure. Okay. Now we've increased the concentration of oxygen by decreasing the volume. We would produce more HGO in that process. So B is a valid answer. C, if you add more mercury, what would happen? Nothing. You're not changing the concentration of mercury. Increasing the temperature actually goes, this is on that side because it's positive. It would go that way, right? Increasing the temperature. Oh, no. Yeah. Increasing the temperature. Actually, increasing the temperature is also a valid answer. Correct? Plus 43 would be a reactant. Unless there's a mistake here and there should be a negative sign. That's a possibility. Because if the key says B is the answer, then D cannot be the answer. And increasing the temperature causes a shift to the right for an endothermic reaction. So that would consume. Oh, there I go again. That would consume HGO, right? So increasing the temperature would not increase HGO, it would decrease HGO. I'm having a bad day on this one. What if we remove some oxygen? That would consume HGO and not increase it. Okay, so after all that being said, the only right answer here is B. Reduce the volume of the bulb, you increase the amount of HGO. All right, I better get away from that one before it kills me. 21. Okay, at 500 K, 1 mole of gaseous ONCl. That looks to me like it might be ONCl. I don't know. It's probably a yeah, it's a type 3 compound. It's placed in 1 liter container. 1 mole in 1 liter, so we have 1 molar concentration of ONCl. Based upon this reaction, nitric oxide and chlorine.
Okay, so we got that balanced equation. And we start off with 1 mole in 1 liter. Okay. If we're going to have to calculate the equilibrium constant, which is here, then we need to know concentrations at equilibrium. But all 3 of these are gases. So what we need in this case is an ice table to keep track of where things are changing.
All right, so what's the initial change equilibrium?
The initial concentration here is 1 mole of gaseous ONCl.
1 molar. There's none of this, and there's none of that.
At the beginning. Okay, but we also are told at equilibrium, this gas is 5.3% dissociated. So 5.3% of it changes into products, right? So if we lose 5.3%, which would be what? Well, what's 5.3% of 1? 0.053.
Molar. So that leaves us with what? 0.947 molar.
That's what's left over. So what do we got over here? Well, this is 2 to 2. So for every 0.053 molar of this,
You have to add that much.
but for every 2 of these, you only get 1 of those. So it's actually half of that value. So I have to get my calculator for that one. 0.053 is 0.0265.
All right, so now we have this much 0.053 and 0.0265 molar.
Now we have the equilibrium concentrations. And we can calculate the K.
So the K is going to be NO squared and chlorine to the first power divided by ONCl squared. So we have this one, 0.053 squared and 0.0265 to the first power divided by 0.947 squared.
All right, so we need to do some quick calculations here. So I'm going to square that one and multiply it by this one. And then that one. And then I'm going to square this one and divide it into that one. And I get 8.3 times 10 to the minus 5. And notice there are no units there. Remember that? You don't put any units. Because of all these powers invoked, you just get units all over the place. So that's why the answer is A, 8.3 times 10 to the minus 5. So did everybody follow the logic here? It says 5.3% dissociated, which means 5.3% of 1, which is 0.053. So you lose that much in the process, end up with this, and then you deduce the others based upon the change that has occurred. All right. So let's see, I think I have that one. Yeah, I have 22 on my list. Okay, 22. For the reaction below, Kp equals 1.16 at 800 degrees Celsius. Calcium carbonate is heated to produce calcium oxide plus CO2. All right. If you've ever visited a cement factory where cement is actually produced, that's the way they do it. They take limestone, grind it up into a powder, and then they heat it. I don't know if it's exactly 800 degrees Celsius, but it's very high temperature. And they use these big rotary kilns, just like this, that are being heated. Just keep it mixed. And it evolves carbon dioxide and produces calcium oxide, which goes into Portland cement. So the reaction, it looks like the reaction is favored slightly toward products, right? 1.16 for the product. The reaction itself is driven to the right by that, plus the fact that you're continuously removing carbon dioxide, right? As a gas in an open kiln, where does that gas go? Out, to create more global warming. So that's the reaction. These are the conditions. What's the question? What percent of calcium carbonate will react to reach equilibrium under these conditions? 31.3 grams of calcium carbonate in a 10-liter container and heated to 800 degrees. Okay, now in this case, the vessel is sealed. All right, so we have a chance to reach equilibrium here. In an open kiln, you never reach equilibrium. All right, so we have calcium carbonate, solid, yields calcium oxide, solid, plus CO2, gas. All right, so what's the expression for the equilibrium here? Well, Kp we're given is 1.16, but what's that equal to? That's equal to the concentration of CO2. Because that's the only thing in there that changes. Solid doesn't change, solid doesn't change. It's only the CO2. So when we put 31.3 grams of calcium carbonate, and that's in a 10-liter container, okay, and at 800 degrees, can't even write, 800 K, no, degrees C. What percent of calcium carbonate will react to reach equilibrium? All right, so when it reaches equilibrium, really what we're looking at is the atmospheric pressure of CO2. So this concentration will be 1.16 atmospheres, right? Now, how are we going to get back from here to here? Remember what I've always said, beginning first semester. You can't go anywhere in a balanced equation, assuming this is balanced, right? One oxygen, two, one carbon. Oh, yeah, it's balanced. Sorry. You can't go anywhere in a balanced equation unless you got moles or gas pressure. But you can only go
pressure-wise from side to side if both gases are on both sides, but we don't. We have solids on this side. So we got to find moles before we can come back over here and do our stoichiometry. So you've got this many atmospheres, that's pressure. You've got temperature here, and you've got volume. We can find moles, right? Remember? PV equals nRT. Number of moles equals RC. PV over RT. So what's the pressure? Pressure needs to be in atmospheres. Volume in liters. R is 0.08206 with these units, atmospheres, liters, moles, Kelvin, and temperature, which will be, is that right, 800 C? Yeah, we need to add 1073. Okay, now we can find moles. So moles is equal to what? Calculator time, 1.16 times 10 divided by 0.08206 and divided by 1073. So that's 1.317 times 10 to the first power. All right. So we know that many moles of CO2. How many moles of calcium carbonate is required to produce a mole of carbon dioxide? 1 to 1. So that is also the number of moles of calcium carbonate. So now, how would you find out how many grams that we consumed? You need molar mass, don't you? So what's the molar mass of calcium carbonate? I have to add it up. Calcium is 40.08. Carbon is 12.01. 3 times 16 is 48. So that's 9, 0, 10. 1 and 9 is 10. See, I did that right. 9, 10, 5, 6, 10. 100.09 grams per mole. So this moles working backwards. Grams per mole is 100.09. There we go. So 1.137 times 10 to the minus 1 times 100.09 is 13.2 rounded off. Right. 3 places. 13.2 grams. So is that the answer? What's the question? Determine what percent of calcium carbonate will react. Okay, now we need to calculate percent. 13.2 reacted out of a total of 31.3. Right? %. 42.1 actually. All right, so that's why the answer is B. Any questions? That was a long way around the barn, of course. But some problems are like that. You just have to break them down into small pieces. Put the information up that you know. Right? This is critical right here. The fact that there's only one term in that means
since it's Kp, that value is actually equal to that value in atmospheres. That's probably the major stumbling block there. Recognizing that fact. See, I think I'm scooting too much. There we go. All right. So that was 22. Let's skip over to 24. Let's see. All right. Looks like we're Haber again. (24). So nitrogen reacts with hydrogen to form ammonia. We know that one. N2 plus 3H2 yields 2 ammonia. All right. Now, what are we given? Temperature is 200 degrees. All right. In a closed container. 1 atmosphere of nitrogen is mixed with 2 atmospheres of hydrogen. So I think we're going to need an ice table. Things are going to change because we're given initial conditions here. 1 atmosphere is mixed with 2 atmospheres. At equilibrium, the total pressure is this, right? So we are given some more information, but in order to make sense of it, I think we need an ice table. So what are the initial conditions? 1 atmosphere of nitrogen is mixed with 2 atmospheres of hydrogen. Oh, only 1, sorry. All right, and initially we have none of that. Okay, then there's a change, and then there's equilibrium. So what are we told? The total pressure at equilibrium is 2.2 atmospheres. So the total pressure, if we add all these together at equilibrium, we get 2.2 atmospheres. That's everything that we're given. Now the question, what's the partial pressure of hydrogen gas at equilibrium? So what's this one? So how do we find that? Well, you have to know what this one is and that one is to subtract it from this one to give you that one. So if we say during the reaction, we're going to lose some of this and lose some of that. Okay? So let's say we, I don't know. If we make this X, we're going to lose some of that. How much of this are we going to lose? We lose 3 times that much, aren't we? Okay. Let's see, did I balance that correctly? 2 nitrogens, 6 hydrogens. Yeah. Over here, we're going to lose twice that much. No, we're going to add, excuse me, we're going to add that much. Okay. So at equilibrium, we're going to have 1 minus x here. We're going to have 2 minus 3x here. And we're going to have 2x there. Okay? Now you're probably thinking, oh boy, we're going to have to stick this into a equilibrium expression, and we're going to end up with a quadratic and have to solve that quadratic. No, we're not. Look what we've got. That plus that plus that equals that. We've already got our equation.
1 minus x plus 2 minus 3x plus 2x equals 2.2 atmospheres.
Now we need to just solve for x, right? And these are all additive, right? Here's a 1 plus a 2, which is 3. And then here x's. So we have a minus 1x and a minus 3x is a minus 4x and a plus 2x. So it's a minus 2x total, right? What's x? X equals, I'm going to do 2 steps at once. 2.2 minus 3 divided by minus 2. See what I did? Subtracted 3 over here, and then I took that minus 2 and divided. So now we know what x is. 2.2, enter 3, minus, and then 2, divide. I got 0.4. 0.4 is x. So now we plug in here. So 0.4 times 3, change the sign, and then add 2. 0.8. So this value is equal to 0.8 atmospheres, which is B. Now, sometimes these problems do develop into massive quadratic headaches, or polynomial headaches, I should say. But in this case, it was very simple. And the reason it was is we were given that final value. If we had not been given that value, then we would have had to solve this using that equation. The problem is we're not given a k value, right? So if we're not given the k, then we couldn't solve that one either. So this problem would be unsolvable. We either need the k or we need that value. Now that we know what each one of these is, right, 0.8, and then we can solve for the rest of them, we can calculate what the k is, can't we? Let's do that. 1 minus x would be what? Here's x. So this would be 0.6, correct? Right? 0.4 subtracted from 1. And then 2 times 0.4 is what? 0.08. Oh, 0.8, excuse me. 0.8. There we go. 2 times x. Now we can calculate k. So k, rather than write it all out, would be this term squared. Where is it? Over here. 0.8 squared. And then we would have this term, 0.6 to the first power. And this term, 0.8 to the third power. So we can calculate k under these conditions. 0.8 squared. Whoa, wait a minute. We can make this a lot easier than having to search for the buttons in the calculator. Look at here. 0.8 to the third, 0.8 to the second, which means what? Cancel this one, and that cancels that one, which makes it 1, divided by 0.6
times 0.8 to the first power, because that canceled this one, left you with 1.
Now that's a lot easier. 0.6 times 0.8, and then take the reciprocal. 2.08.
This would actually be what?
K sub P, because we're using atmospheric pressure. Okay? That wasn't part of the problem, but I couldn't resist. Okay, let's see, where were we? Coming up on 25, is it? 1 atmosphere, yeah, 25. Initially, 2 moles of nitrogen and 4 moles of hydrogen were added to a 1-liter container, and the following reaction then occurred. Okay, that's Haber. The equilibrium concentration of NH3 equals 0.55 moles per liter at 700. The value of K at 700 for the formation of ammonia is, okay. So we are gonna have to do some fancy footwork on this one.
25.
And we're going back to Haber. I'm going to write it the way they did. And these are gases. I haven't written it in there, but they're all gases.
Okay. So what are the initial conditions?
2 moles of N2, and it's all in 1 liter container. That makes it convenient. 2 moles of N2 means 2 molar. Let's see, we got, oh, Cody showed up. All right. Okay, back to the problem. 4 moles of hydrogen
In 1 liter, which is 4 molar.
Okay. And let's scooch this up a little bit. There we go. 4 moles, 4 molar, 1 liter, this reaction. The equilibrium concentration of ammonia equals 0.55.
So a change has occurred, we reached equilibrium, and we're actually told
The concentration of ammonia.
0.55 molar.
Okay. And the temperature is 700 degrees C. I don't think we need that.
So what do we have here? Well, how did you get that? Well, you had to add it, right? Because this is 0. So that's this one, 0.55 molar. So if you get 2 of these,
How many nitrogens were required? Half of that, right? 1 to 2. So if that's 2, then 1 would be half of that. .275.
right? Now, if that's 1, then this has to be 3 times that.
Right? So 3 times that value is 0.825.
0.825. Okay, and that's subtracted, right? Because we're going this way.
There's nothing over here, so it has to go that way. That's negative, negative, positive.
All right, so what's this value?
2 minus 0.275. Well, let's go ahead and do this one. This one's already in my calculator, so I'm going to do that one first.
3.175. Okay. And let's see, 0.275 and 2, 1.725. 725.
Okay, this was turning out easier than I thought it would. Now that we have these values, we can calculate the
K. Right? We just take this one squared. Right? Because of that value right there. Products. Divided by reactants. This one to the first power. And this one, oops, sorry. This one's to the third power. This one's to the first power. There we go. Okay. Reactants.
First of all, did I put those in the right order since I wrote it the way they wanted? 2 molar nitrogen, 4 molar H2. Correct. Okay. So now we can calculate, get that value. So 0.55 squared, and then 3.175 enter cubed 1.725 times, I think it's 5.5 times 10 to the minus 3. Yep. Using concentration units this time instead of partial pressures. Oh, I wish I'd have kept that other number. Trying to remember. I can't remember it now. Unless it's still hanging in my calculator. Now, what I was going to do is, we calculated the K for this one, and we calculate the K for the one before it. But that was in partial pressure, and I was going to compare one to the other using our formula, right? The one that's in your useful information should be there. Let's see. Where we relate K. Oh, is it not there? Ooh, that's mean of me not to put it in here. Oh, there it is. Where K sub P equals KEQ times RT to the delta N power. We could have made that. I wonder if I can go back and do that. 24. Yeah. Let's see. 11 o'clock. Do I have time to do that? Let me see. I don't want to miss getting all the. We'll come back to it. If we have time, we'll come back to that one. We'll have to. This one is in the answers, and the other one we have to calculate. So if we have time, we'll come back to that one and compare the K values using that formula. My guess is that it's all hypothetical, so the K values are not going to jive. Let's see. All right. So the next one I've got, we just did 25, 26. Okay, 26. This is sort of a combination chemistry algebra. All right. So first of all, let's review the rules for manipulating equations and the effect that it has on the K values.
If you have an equation of, well, I don't know, say A yields C, and you say, what's the K for that one? Well, it's going to be big C to the C power, and then big A to the A power.
Okay? If you multiply this by some factor, well, so let's flip it first.
If you flip the equation, it just inverts K. So the new K would be K to the minus 1, that would be 1 divided by K. So if you flip the equation,
You take the inverse of the K.
if you multiply by a factor, then that factor goes up here and here, which means now the new K is equal to the old K
To the X power, because that X factors out as a power of that expression. Okay, we did that in lecture.
What I didn't do was prove to you what to do if you have a K for this one, and then you have maybe a second equation, and you add them together. What do you get? Well, you get the A plus the B yields the C plus the D.
Right? So if you add those two together, like we were doing with Hess's law, what happens to the K for this expression?
Well, what's the K for each one of these? The K for this one is,
Yeah, that was getting dim. Let me get one that's got a little more bounce to it.
this one on top, this one on the bottom, then this one on top, and this one on the bottom.
Okay, so what's the one for this expression? So this total K, where you add them together, that's getting too weak too. You'll find one that works.
This would be big C to the C power and big D to the D power divided by A to the A and B to the B.
So if you add these two equations together to get that one, then how do you arrive at this one from those two?
Notice that this one is equal to K1, and this one is equal to K2.
So when you add two equations together,
You multiply.
the K's. Okay? Now, that being said, 26 is a Hess's law type, only we're not interested in the enthalpy of the reactions. We're interested in the K's. But if you can add equations together in Hess's law to find out what the total enthalpy of the target equation is, I don't see any reason why you can't also add those equations together as long as you know what to do with the K values. I mean, you're still adding equations together, and that's valid. It's state function. K's are state functions, right? They don't care how you got there. Once you reach equilibrium, that's your state. You got a K.
So let's go in and find out what it would be for these hypothetical reactions. Well, actually, these are real reactions.
The K's are the hypotheticals. So we've got, I'm gonna have to get a fresh one here. Hold on a second. Go to my stash. There we go. 26. So we've got these two reactions here, this one at K1 and this one at K2. And we're going to add them together in some form to equal this final, our target equation. All right. So let's write down the first one, 4 coppers. Plus 1 oxygen yields 2 copper 1 oxide solid. And that has a K. Let's see, let's scoot. Get back over here. There we go. All right. So let me put the target down at the bottom so we can keep track of what we're trying to do. So this is where we're headed. 2 coppers plus oxygen gas yields 2 copper 2 oxide solid. So we want to know what this K is. So for this one, we've got a copper on this side and a copper on that side. That's good. So we're probably going to leave it as is. We're not going to flip it. So let's see what's the other one. 2 copper oxide. 2 copper oxide. And oh, that yields Cu2. Okay, I will have to change that one just a second. Let me get this one up on the board. 1/2 oxygen gas. And this one has a K2. Okay. What just occurred to me was there's 4 copper here and we only need 2. Correct? So we got to take half of that equation. So now we have 2 Cu plus 1/2 O2 yields 1 Cu2O. What happens to the K? It's raised to that power. All right. So this equation we're using along with its K. All right. How about this one? Well, let's see. We don't have Cu2O anywhere in this equation. But we've got it on this side for that one and on the same side for that one. So this means it has to flip in order to cancel that one out. So if we say Cu2O plus 1/2 O2 yields this one, 2 CuO. Now what happens to this one? When you invert the equation, you take the inverse of the K. So this one is now 1 over K sub 2. Okay. Now, before we go any further, let's see what's happened. Can we cancel? Do we have what we need in the end? Well, this one is on this side, it's on that side there, so that one cancels. Now if we bring this down, here, here, we're good. This one plus this one is that one. Okay? And on this side of the equation, here, because we're using this one and that one, we've used all these terms. Now we've got this one left. 2 CuO, 2 CuO. Okay, so our target equation is the valid summation of these manipulated
equations. Now we need to multiply this one times this one. So now that K is going to be K sub 1 to the 1/2 times 1 over K sub 2. So K to the 1 to the 1/2 over K sub 2 equals our new K. And the answer would be E. K sub 1 to the 1/2 divided by K sub 2. Okay, that's how that works. All right. My board's scooting again. Here we go. That was 26, 28. All right. Let's see what we got here. Got an hour left. Exactly 1 mole of N2O4 is placed in an empty 1 liter container. So the concentration is 1 molar initial. Allowed to reach equilibrium by this equation. N2O4 dissociates into 2 NO2s. If at equilibrium, the N2O4 is 37% dissociated, what's the value of the equilibrium constant for the reaction? All right, so this is kind of like the other one, but we'll do it for practice. So we've got this equation. Okay. Our initial concentration is 1 molar, correct? 1 mole in 1 liter. And this is 0. Change, equilibrium. So what else does it tell us? N2O4 is 37% dissociated. So we're going to lose that much in molarity. Right? We know it's going that way because that's 0. So if we lose 37%, 37% of 1 is 0.37. So that means we have 6.3. Okay? And if we lose that much over here, we have twice that much over here, 1 to 2. So it's 0.74. 0.74. Oh, this is too easy. What's the K? Well, the K now is this one squared. Divided by this one. I get 0.87. Is the K value. So that's why the answer is E.
All right. And 29. Let's see. We dispatched 29 fairly quickly. I think so. 29. Okay. Our reaction is hydrogen plus iodine yields 2HI. We had one of those before. And the K equals 44.8 at some high temperature. Okay. Let's see what we come up with.
So we've got hydrogen gas plus iodine yields. By the way, this is a gas.
Are they saying at a high temperature? Okay, so at a high temperature, we're saying yeah. At a high temperature, it's very likely iodine is a gas. Okay. So K equals 44.8. Which means the equilibrium is way over here. Equimolar mixture of reactants.
Equimolar mixture of reactants. So initially, we have X here and X here, nothing there. So change equilibrium.
Gives the concentration of the product to be 0.5 molar.
0.5 molar.
Okay. Determine the equilibrium concentration of hydrogen.
So this is what we want to know. So how did we get here? Correct? Has to move that way. And if you got two of these, how many of these did you lose? Right? Minus what? Half of that, correct? 1 to 2. Okay, so what we have here is we want the equilibrium equilibrium concentration of hydrogen. So the term we're looking for is this one. All right. So now we know that K is equal to this one squared divided by these two times each other. So they would be squared. That one times that one. And that's equal to 44.8. Now we have a decision to make. You know what? Let's make, since this is the term we're looking for, let's make that equal to y. Right? Y and y. So what that does, since we want to know what that is, why do we need to bother with x and then subtract 0.25 from it? What we really need to know is, what is that value? Right? So that's the value we're looking for.
That simplifies things a whole lot. Now we don't have to deal with a quadratic, because x minus 0.25 squared is going to give us a quadratic expression.
So let's just go for that value. Right? So what does that mean? That means that y squared here is equal to this term divided by 44.8.
Okay. All right, so 0.5 squared should be 0.25. Yep, 0.25 divided by 44.8, which is 5.58 times 10 to the minus 3. Well, I'll go ahead and write that in.
5.58 times 10 to the minus 3.
But what's y? Y is the square root of that.
Right? So if we take the square root of both sides,
We'll get y equals that term. 7.47 times 10 to the minus 2.
so this value, concentration of hydrogen at equilibrium, is equal to,
What did I say? 7.47. Two significant figures.
7.5 times 10 to the minus 2 molar.
Yep. That's why the answer is E. So the trick here is to recognize that we really don't care about X. We only care about that whole term, which made the calculation much simpler. Let's see. All right. So let's see, where are we? 29, 30. We have 45 minutes left. Let's see. Considering the following reaction, 2HF yields H2 and F2, and the K is this value. We start off with 1 mole of HF, 0.362 moles of H2, and 0.75 moles of F2 in a 5-liter flask. What's the reaction quotient?
This is very simple, straightforward.
You have this reaction, and they're all gases, so I'm going to leave the gas term out.
H2 plus F2.
Now, does it matter what K is? No, not to answer this question, because all it asks for is what's Q. Right? So how do you determine Q? Well, you use the law of mass action, only it's a non-equilibrium situation.
So Q in this case would be H2 times F2 divided by HF squared.
Okay? So we just plug in the numbers, but we have to know what the numbers are. 1 mole of HF in what size flask? 5 liters. So what's the concentration? 1/5, 0.2 is HF. How about hydrogen? Hydrogen is 0.362 moles in 5 liters.
362 divided by 5. And fluorine is also divided by 5.
But it starts out at 0.75.
0.75.
So now we can do the calculation. We just have to say 5 into that one, 5 into that one.
And then this one squared.
So I get 0.272. All right. That answers the question. Which direction is this reaction going to go? Q is 0.272, and K is equal to 1 times 10 to the minus 2.
So 0.010.
If Q is bigger than K, that means we've got too much product. So it's going to move back to the left. That wasn't part of the question, but interesting to know. Actually, that wasn't 3, that was 30. Number 30. All right. Let's keep this centered. There we go. Okay, that was 32. Carbon disulfide and chlorine react according to the following equation. When 2.14 moles of carbon disulfide and 5.85 moles of chlorine are placed in a 2-liter container and allowed to come to equilibrium, the mixture is found to contain 0.62 moles of carbon tetrachloride. How many moles of chlorine are present at equilibrium? Let me see. We have time to work this one. Actually, we do. So let's put the, this is 32. Need to stretch it out a little bit because there's lots of terms in here. Carbon disulfide plus
Chlorine.
and
Disulfur, dichlorine, dichloride gas.
plus, see, 3 of those, that's good.
And 1 carbon tetrachloride.
There we go. So what are the initial conditions? All right. We have 2.14 moles of CS2 in a 2-liter container. All right. And 5.85 moles of chlorine.
5.85 moles in a 2-liter container.
And the mixture is found to contain 0.62 moles of this one.
So there's a change and then there's an equilibrium.
And at equilibrium, the carbon tetrachloride is 0.62.
0.62 moles in 2 liters.
All right. So what's the concentration here? 1.07 molar. This one, so let's see if I can do this one in my head. Let's see, 2.925
This one's 0, that one's 0. Initial. What's the change? Well, how did we end up with this one? We ended up with that one by adding that much. Well, actually, it's concentration-wise is 0.310 molar. So we had 0.310 molar. So this is 1-to-1 relationship, correct? So that means we had to add that much here also, 0.310 molar. This is 1-to-1, so we actually lost that much, minus 0.310 molar. This is 3 times that, 0.930 molar, minus. Okay, so what's the equilibrium concentration for each of these? What's the question? Let's go back to the question so we don't spin our wheels. How many moles of chlorine are present at equilibrium? So we want to know this one right here. 2.925 minus 0.930 equals what? 1.995 molar. But that's not how many moles, right? That's the molarity, and that's spread out over 2 liters. Right? So what does moles mean? It means moles per liter. If we multiply by 2 liters, we get the number of moles, 3.99. Or, yeah, that's right, 3.99A. Okay? That was 32. Let's see, what else do I have marked off here? 30, 33. Oops, go down. Okay, I think we can make it. 33. At minus 80 degrees Celsius, the K for the reaction of N2O4 yields 2NO2 is 4.66 times 10 to the minus 8. So at that temperature, N2O4 is favored by a huge amount. So we introduce 0.047 moles of N2O4 into a 1 liter vessel, right? So that's 0.047 molar. And let the equilibrium be established. The total pressure in the system at equilibrium will be what? Okay, 33. So we have this equation, N2O4 gas yields 2NO2 gas. Right? So both terms are involved in the equilibrium, and both pressures must be known to find the total. All right, so K, let's see, temperature is minus 80 degrees C. K is equal to 4.66 times 10 to the minus 8. Okay, I'm putting everything we know up here. 0.047 moles of N2O4 in 1 liter, which makes it that molar. Okay, that's everything we know, I think. What's the total pressure? All right. So we have a change and we have equilibrium. So what's going to happen? It's going to go that way, right? Because that's 0. So we're going to lose, let's just say we lose x here. And we add 2x over here, right? 2 to 1, minus 1x plus 2x. So we have 2x over here. Now the equilibrium expression is NO2 squared divided by N2O4 to the first power, which means we have 2x squared divided by 0.047 minus x. And that's equal to 4.66 times 10 to the minus 8. Okay. So we know, we know we're going to get a quadratic out of this if we go one direction. But if we choose to estimate, then we might be able to eliminate the quadratic. So look, if the equilibrium is 10 to the minus 8, that means that not very much of this is produced. That is, you don't get a lot of it shifted over here. That means you didn't subtract a whole lot down here. Very small amount. So what that tells me is that this term right here is much smaller than that one. So we can estimate at 2x squared divided by 0.047 and just eliminate that x. Now if we solve for x, we only have to deal with a square root eventually. So let's say this times that is equal to this, which is what, 4x squared? So we'll say 4 divided into that. We took this one times that one, then we're going to divide by 4. Now we need to take the square root of both sides. So x is 2.34 times 10 to the minus 5. So were we correct? Yeah, 10 to the minus 5 is a lot smaller than 10 to the minus 2. So we were correct. And we could do the calculation for a 5% rule, but I guarantee it's going to be less than 5%. But the answer is we haven't got there yet. What we need is the total number of moles. This is the molar concentration of that one. The molar concentration, excuse me, that's not the molar concentration. This one is equal to 0.047 minus that. So that's basically 0.047. 2 times this one is what? 2 times that value is 4.68 times 10 to the minus 5. 4.68 times 10 to the minus 5. Then we add this one back to that one. Now, why am I doing that? Because in order to calculate the total pressure, I can use the total number of moles of gas in this container, and then the ideal gas equation will give me the pressure. So what's the total number of moles, right? Because ideal gases don't care what kind of gas it is. They just care about moles. What's the number of particles? So this one plus that one is essentially that one. 0.047 moles. Okay? Now that we know that, we can calculate the pressure. So I'm going to erase this to give us a little room right here. So if we're going for the total pressure, PV equals nRT, solve for P, nRT divided by V. So the number of moles is 0.047. R is 0.08206. Temperature, what's the temperature? Minus 80 plus 273. Right. So that's 193 K. Divided by volume.
What's the volume? 1 liter.
There you go.
So we just say 0.047, 0.08206, 193. We have 0.74 atmospheres. Why do I know it's atmospheres?
Because of that term right there.
Because of the constant. That means the answer is B. Let's see, I got 2 more and a half hour to do it. So I think we can make it. 34 I'm going to do next. All right. Let's scroll down to 34. A solid sample of NH4NO3. What is that? That's one of those compounds that's made out of 2 polyatomics. Ammonium nitrate. And that product is highly restricted for sale in the US above a certain quantity, because you can make a neat little bomb with ammonium nitrate and a little fuel oil. Right? In fact, the mining industry uses prepackaged, they call it ANFO, ANFO, which means ammonium nitrate fuel oil. Comes in bags, and they pour it down their boreholes and set it off, and it magnifies the explosion of the stick of dynamite by 10-fold. Okay, a solid sample of NH4NO3 was placed in an evacuated chamber, right? No pressure to start with, and then heated so it decomposes into N2O and H2O. At equilibrium, the total pressure in the container was found to be 2.63 atmospheres at a temperature of 500 degrees C. Calculate Kp. All right. Let's see. This is probably not going to be as difficult as it looks.
So NH4NO3 solid yields N2O gas plus H2O gas.
All right. So what did we start with? Oh, okay. At equilibrium. At equilibrium, the total pressure was found to be 2.63.
The total then is 2.63 atmospheres.
All right. So we're assuming from the information that's given us that the decomposition of this solid was virtually complete. So in effect, it's not really an equilibrium calculation. This is a stoichiometry problem. But it does want to know what the Kp is.
So the Kp is equal to, that doesn't count, just those two. Actually, the Kp is the partial pressure of N2O to the first power times the partial pressure of H2O squared. Okay? So if all of this turns into that, then if this is X at the end, then this has to be, where did they come from? Well, that's plus X. So this had to be twice as much, 2X. So X plus
2x is equal to 2.63, correct?
So if we do that, then we say this is 3x, so x is equal to 2.63 divided by 3, which is equal to
0.877.
Okay? So if that's true, then 2 times that equals what?
1.753.
1.753 atmospheres, right?
Because the number of moles of a substance is proportional to its partial pressure if it's a gas. Right? So even though this expresses molar concentration or moles of the gas, actually, because it doesn't say what size the container is, but the container size didn't change. And right, Avogadro, that's the one I couldn't remember a while ago. Avogadro says if all those conditions are the same, temperature, pressure, well, the pressure is going to change. So the pressure and the number of moles change with each other. Direct proportion. So now we know that the pressure of this one is that, and this one is that. So we can just plug the values in. Kp then is N2O, which is X, 0.877. And then this one is 1.753, excuse me. Squared. Okay. So we'll take that one and square it. Here we go. And then 0.877 times that. 2.70. That's the K sub P for this reaction, given that data. Okay, I think I got one more. I don't think we're going to have time to go back to that other one. So we'll just be sure we
Get this one right. 36. Okay, at a certain temperature. So temperature doesn't matter because why? Because it's going to stay constant. Temperature won't change. K for the reaction of 2 nitrogen dioxide yields dinitrogen tetroxide. The K for that is 7.5. 7.5. If 2 moles of NO2 are placed in a 2-liter container, permitted to react at this temperature, and notice that the K is given for this reaction in this direction. Before we were looking at the decomposition of N2O4. Here we're talking about the synthesis of N2O4 from NO2. Right, so that's important for how to interpret the K. The K would be different if it were reversed. So let's write that up here. What do we know? 2NO2 yields N2O4. And those are both gases. And the K for this equals 7.5. Okay? If 2 moles of NO2 are placed in a 2-liter container, which means 1 molar, and permitted to react, calculate the concentration of N2O4 at equilibrium. So we're starting off at 0. There's a change. At equilibrium, we want to know that value. All right, so what happens? Well, it's headed this direction, which means if we add this as an x, that means we had to subtract 2x. Notice how I chose my x, because x is our answer. And this is 1 minus 2x. Okay? So we still want to calculate the concentration of N2O4, that value. So K then is equal to this one. Pardon me. Sorry about that. And this is divided by NO2 squared. So if we plug in our values, then N2O4 is x, and 1 minus 2x is squared equals 7.5. Okay, so what can we say about this equation? It's going to be difficult to eliminate the x because this value is so far to the right. There is a significant amount of x produced. That means we lose a significant amount over here. We cannot ignore that 2x. Right? So we have a choice. Are we going to do it by quadratic, or are we going to use successive approximations? Well, in the worked problems, I use a quadratic because that gets you straight to the answer. But what if we do successive approximations? Okay, let's try that route. You've already got. So what are we going to have to do? We're going to have to do the quadratic. Wait a minute, 7.5. All right, so we'll do the quadratic. I got 7 minutes, right? So let's go ahead and do the quadratic. I'll have to figure it out later.
why the approximations didn't work. All right, so what is this term right here? Well, it's going to be 7.5 times whatever this term is. So 1 squared is 1, and minus 2x squared is minus 4x squared, is plus 4x squared. Okay, and then 1 times this one and 2 times that one would be minus 4x. Correct? Expanding the polynomial. Yeah. Okay, and that's equal to x. So we have 7.5 minus 30x plus, plus 30x squared equal x. And we subtract x from both sides. And let's put it in the order, a quadratic order. So this is unchanged, 30x squared. And this is a minus on this side, so it'll be minus 31x plus 7.5 equals 0. Now we can use our quadratic. All right, this is A, B, C. The quadratic says that, let's see, minus B plus or minus square root of B squared minus 4AC over 2A. So it's going to be X equals minus B. So a minus 30 plus or minus the square root of B squared, which is minus 30 squared, minus 4 times A times C. And this is all divided by 2 times A. Okay, let's see if I put those in right. There's B, minus B plus or minus. There is B also, squared this time, minus 4AC. And then 2 times A. Okay. So what would it be with a plus? Well, let's resolve this one right here. Then we can do plus minus. So 30 squared is 900. I know that. And then this is 120 times 7.5. Well, that doesn't make any sense. That gives us 0. I did something wrong. What did I do wrong? That's right. 30x squared minus 30. Oh, 30x squared minus 30, 7.5, 5 minus 31, 30x. That's true. Oh, B is 31. There we go. Now it'll work. So let's do this again. 31 squared is 961, and 7.5 times 30 times 4, subtract is 61. So this is 61, and the square root of 61 is 7.81. 7.81 is that term. So now we have a positive 31 plus 7.81 divided by 60 is minus 6.47. No, 0.647. The other way we have 7.81 is subtracted from 31. And then divided by 60. That's 387, 0.387. So those are our two choices. What did we start out with? We started out with 1 molar NO2. So if we say and we're trying for, if that's X, then what's the other one is 1 minus 2X, right? The concentration of NO2 was 1. So the concentration of NO2 afterwards would be 1 minus 2X. 1 minus 2X. So not just the X has to be valid, which those are valid numbers for X. But 1 minus 2X has to be valid too. So if we say 0.647 times 2 is minus 1.294. So 1 minus 1.294 will give you a negative number. That can't be. So this has to be the answer. And I can't for the life of me figure out why it didn't work the other way. I'll look into that and either add it to the video for this or talk about it next time. Okay, so that's it, and I'm out of time. Any comments, questions? Let's see. Do I have a lab thing after this? Yeah. I should be in it right now. So we'll have a lab tutorial right after this. So I'll shut this thing down. We'll stop the share. And I'll reappear at the Chem104 lab tutorial.